Alright, boys and girls, welcome back to the drive-through. So we move along our pre-calc journey, and we're sticking with vectors here. Now we're going to start applying these to things, and obviously that is the entire point of math, and we're getting into some higher-end stuff, so hopefully you guys will find this to be interesting. There's like the math of this, which is so silly easy. 2, 5 plus 10, 1 equals what? And that's as easy as you think it is. It would be 12, 6. Okay, now let's look at what does that mean geometrically? Okay, so remember that vectors have no position. They have a direction and a magnitude. So 2 over 2 up 5 is going to go to there. Let me go ahead and get a nice little vector thing here. So there's 2, 5, and then 10, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10, 1. Now, what does 2, 5 plus 10, 1 give you? Well, since they have no position, I could take this vector. That's literally what it means. I could do 2, 5 and then add 10, 1, and the result I'm going to put in this purple vector. No, don't do it. Don't do it. I'm going to put in this purple vector. And that's the geometric interpretation of this problem. So you can think of the answer as the diagonal of a parallelogram. Okay, if you thought about this shape like this and that the answer to the question is a diagonal to the parallelogram. But what's really going on here is, if you think of this, let's say we had some motion that was represented by the black vector, and then we had some motion that was represented by the red vector. The resultant motion, if those two things were combined, would be represented by the purple vector. And this has a tremendous amount of applications scientifically. So let's look at this one. Now let's consider two tugboats that are pushing an oil tanker into a harbor. The tugboats are unable to push with complete horizontal force due to the spatial constraints. So basically, these tugboats can't get right behind the boat because they would like run into each other. So if I could kind of just expand the picture, they've got to push at an angle. Now luckily these tugboat captains are smart, so they're pushing at a symmetric angle. And so what we're going to do here is we're going to break down these into vectors. We're going to figure out how to turn these into vectors. So the force is going 400 pounds. Is it pounds? Oh, yeah, I missed that. So this tugboat is pushing with 400 pounds in that direction, and the other tugboat is pushing with 400 pounds in that direction. Okay? What we need to do is break up the horizontal component of that force. That's going to end up being all that matters. Okay, but we will break down both components. So this would be the vertical component of that force. Since these are both being pushed at a 20-degree angle, you can use trig to find the red vector. Okay. Now I'm gonna do it by hand. So we would say, according to the 20, x is adjacent, 400 is hypotenuse. You would say cosine of 20 is x over 400. So notice that is where, oh, this would be a negative 20. Thank you. This one is a positive 20. So this is where this comes from. And then notice y is 400 times the sine of negative 20. I'll go back above. X is 400 times the cosine of negative 20. So I can break this vector up using trig. The answer is 400 cosine negative 20, comma, 400 sine of negative 20. And then we can break x2 and y2 up by just calling it 400 cosine of 20, comma, 400 sine of 20. Okay? Now, we want to know what is the resultant vector in this situation. So, we're just going to add these things. Let's bust out our calculator. So, 400 cosine of negative 20 plus 400 cosine 20, cosine of 20, and that's, where's my error at? Did I type in a negative sign? Oh yeah, so delete that. Enter. So this is 751.75. Okay. Now, let's do the same thing with our sine. So, 400 sine of negative 20 plus 400 sine of 20. 0. So why did that happen? Well, if you think about it, there's a lot of force being pushed on this boat. However, this horizontal force adds to that horizontal force to get us almost 800 pounds of force. Whereas that vertical force that was pointing downward is completely offset by this vertical force that is pointing upward, leading us to a net zero of vertical force. Well, that's good because we want as much of the force to go parallel to the horizon as we can. So, what did we learn? The tugboats are pushing, because it's the answer to the question, I'm not going to write it out, interpret the resultant vector. The tugboats are pushing 751.75 pounds of force completely in the horizontal direction. That's great. Okay? Let's look at another example. An airplane is traveling at a fixed altitude with a negligible wind factor. The plane is headed, this is just jargon, so don't let this cat you up, N30W. What does that mean? 30 degrees west of north. All right, west of north. So let's just draw a picture. Here's north. So 30 degrees west of north would be that. All right, so let's get this on the axis. I'm going to erase this. I'm going to just plot myself in black, a little XY plane, only this time it's going to be east, north, west, and south. And what we have, let's go back to this one, is something like that, 30 degrees west of north, okay, at 500 miles per hour. So the magnitude is 500. The angle creates a little 30-degree angle there. All right, we'll come back to that. Now, as the plane reaches a certain point, it encounters a wind with a velocity of 75 miles an hour 45 degrees north of east. So, 45 degrees north of east looks like this. Now I'm going to make this one significantly smaller because it's a lot shorter. It's a lot smaller. This is 75 miles per hour. So this is where you just take the geometric interpretation. You're going to add them. Okay, you're just really just going to take this and you're going to make it go there. And I can tell you that helps me a lot because that means that my resultant vector is going to look like that. So I expect that the wind, which is blowing in this direction, is going to take our green course and change it to the red course. So how are we going to do that? Well, 500 times cosine. Now I'm going to do, this is where the reference angles come in. 120 sine of 120. That is going to be our first vector. So let's pop that in our calculator. 500 cosine 120. So that's negative 250, comma. Now look, this is a special right triangle. So I should be able to just go 30, 500. Half of 500 is 250. So this one is going to be 250 radical 3. And this is why math gets hard, is because that's really just a geometry fact there. But luckily we've been reviewing it, so hopefully that makes sense to you. Okay? Alright, so that is the component of our green. So again, if I just go back to our original green vector, you've got, if you break it up into component form, this was 500 in that direction, so that means 250 of it is traveling in the left direction, and 250 radical 3 is traveling in the upward direction. Now, since our blue vector is pointing at a 45-degree angle, their horizontal and vertical components are going to be the same. So if that's 50, this is going to be 50 divided by radical 2, which is 25 radical 2, right? Yep. And this is going to be 25 radical 2. So that will be our second vector. And if I add those up, it's going to give me our resultant vector. So let's check that out. We got negative 250, negative 250 plus 25 radical 2 over, enter. So you get a negative 242.93 comma. Now do 250 radical 3 plus 25 radical 2. And you get 468.36. So, let's see. Our green vector started out as negative 250, comma, 250 radical 3. Then the blue vector pushed it, so the end direction, negative 242, well, I don't need to rewrite it. Notice, if you compare this one, the original, to this one, the actual, it has been blown off course a little bit to the right, if that makes sense. Now, let's use this to get an exact speed. So let's just plot this. Just a rough sketch of this red vector. It's going to be that is what we think. Let's write in the legs. This was negative 242.93, and this was 468.36. Okay, let's find this angle using tangent. Tangent inverse of 468.36 divided by negative 242.93. Second, tangent 468.36 divided by 242.93. All right, I'm going to leave it positive, and I'll tell you why I'm doing that here in just a second. Enter. So you know that theta, this angle, is 62.6 degrees. So, this angle, subtract that from 90, minus 90, and you'll get 27 point, this angle right here is 27.4 degrees. So that is going to be west of north. How fast is the plane going? Well, how fast the plane is going is the magnitude of this vector. How do we find the magnitude of the vector? It's just Pythagorean theorem. Square root of a squared plus b squared, where this is a and this is b, so let's bust that out in our calculator. Square root of 468.36 squared plus 242.93 squared. Why am I not making that negative? Because it doesn't matter. We're squaring it. And you get 527.61. That's miles per hour. So, what did the wind do to the plane? Well, it knocked it off its course, but it actually helped speed the plane up a little bit, because some, and you could figure out how much by doing the projection of u onto v, some of that was going in the same direction as the original green path. I hope that helps. This is why we're learning these vectors. Boom!